Hello everyone, today let's take a look at QP 107 where we have 12 passengers who board the elevator at a ground floor of a 10-story building, and each passenger independently selects one of the 10 upper floors to get off on, and on average, how many distinct floors will the elevator stop to let passengers off? So we need to find on average how many distinct floors the elevator will stop at. So we're just trying to find the expected value of the number of stops that the elevator is going to make, and this is going to be a good question to show why linearity of expectation is so useful. So we know the definition of expected value. We're taking the sum over all the number of possible stops that we could have going from 1 to 10. We can't have 0 because obviously the passengers have to get off on some floor. So we take the sum over all the values that k can take times the probability of that k occurring. And you'll notice that if you actually tried to solve this out just by using this formula right here, it's going to get really complicated. I'll actually try and do it probably at the end of the video. But you'll notice that in this question, we can basically express k as a sum of different indicator variables, and that's just going to make life a lot easier. And we can do that just by having an indicator for all of our 10 floors. So that's going to be equal to 1 when at least one person gets off at it, and it's going to be equal to 0 when no one gets off at it. So for instance, x sub 10 is the indicator that is equal to 1 when at least one person gets off at floor 10, and it's equal to 0 when no one gets off. And then we define the same indicator for 9, 8, 7 all the way to 1, and then you'll notice that when we sum up all these indicators, we can have I going from 1 all the way up to 10 of the indicator x sub I. Well, that's just going to be equal to k, the number of stops that people get off on, right? Now I can just replace k with the summation, so now I'm taking the expected value of the sum of these indicators right here, and then we know with linearity of expectation, that's just going to be equal to the expected value of x1 plus the expected value of x2, etc., right? Now, since all of our indicators are basically doing the exact same thing, we can just find the expected value of one of our indicators and then just sum it up 10 times, and that will give us our final answer. So if we take the expected value of one of our indicators, well, it can only take values 0 and 1, so we have a 0 times the probability that our x sub I is equal to 0 plus 1 times the probability that x sub I is equal to 1. And now let's just calculate this right here because this is going to be canceled, and we'll get our answer. So to get this right here, we just find the probability that at least one person gets off on a random floor. Well, we have 12 different people. The probability that at least one gets off on our floor, we can just write that as 1 minus the probability that 0 people get off at x sub I, right? Well, we have 12 people, each with an equal chance to get off at any of our 12 floors, so the total number of ways that people can get off on floors is going to be 10 to the power of 12. So now of these outcomes, how many of them have our randomly chosen floor? Let's just say it was floor 1 with 0 people. Well, if we remove this from the equation and then we just distribute 12 people now to 9 floors, well, we're going to have 9 to the power of 12 restricted outcomes. So therefore, the probability that 0 people get off on this floor is just going to be our restricted divided by our total. So 9 on 10 all to the power of 12, right? So the probability that x sub I is equal to 1 is just going to be equal to 1 minus this number right here, and then we multiply that by 1, and that will be our expected value for this indicator. But then to get the expected number of total floors that we get off at, we're taking the sum of all of these indicators. They're all 10. They all have this same expected value, 1 minus 9 on 10 to the power of 12. So this right here is just going to be equal to 10 times 1 minus 9 on 10 to the power of 12. Then when you actually find the value of this expression right here, it's going to be roughly 7.17. So we expect that on average, we have 7 stops on our elevator, or about 7 stops. So this right here is going to be our final answer. You can see how linearity of expectation and using indicators just made our lives so much easier, because now I'm going to show you how hard it is just to calculate this straight up without using linearity. So let's just solve this using the actual definition of expectation. Why? I don't know. It might be a good exercise, but it's going to be pretty hard. So k is the number of stops that the elevator is going to make. So let's first find the probability that k is equal to 1. Let's just start off small. What is the probability that there's only one stop? Okay, so we have 12 different people getting off on 10 different floors. So we know that the total number of outcomes is going to be, again, it's going to be 10 to the power of 12. Now we need to find the number of outcomes where basically everyone gets off on the same floor, because that is the only way that k can be equal to 1. Basically, this is going to be Stirling numbers of the second kind question, which we talked about in combinatorics 2, right? I have 12 different people and I want to put them all on one floor. So for everyone to get off on a floor, well, we have 10 different options for the floor that they could all get off on. And when we have 12 distinct people and we're placing them into one basically identical box, it's going to be only one way to do that, but we have 10 different floors. So this is going to be equal to 10 divided by our total outcomes, which is 10 to the power of 12. So that's the probability that everyone gets off on the same floor. The probability probability that k is equal to 1. Now let's look at the probability that k is equal to 2, where that means that the elevator stops 2 times. So our elevator stops on 2 different floors, and we have 10 total floors, so we need to choose 2 of them for the elevator to stop on. So this is going to be equal to 10 choose 2. So now once we've chosen our 2 floors that the elevator is going to stop on, we have to figure out how many ways there are to distribute our 12 people to these 2 different floors. So set partitions, I have 12 distinct objects to distribute to 2 distinct floors, also subject to the condition that everyone can't get off at the same floor because we have k equals 2, right? So we want at least one person to get off on both of these floors. So we can just use inclusion exclusion here. We have 2 options for each of our 12 distinct people, so that's going to be 2 to the power of 12 total options. Now we just need to subtract off the cases where all of these people are distributed to one of our floors. There's only one way to distribute 12 people to one floor, and there's 2 choose 1 different ways to choose which floor is empty, right? So that's going to be 2 choose 1 times 1. So again, for k equals 2, we have 10 choose 2 different ways to choose the floors that people get off on, and then we have 2 to the power of 12 minus 2 choose 1 ways that when we choose these 2 floors to distribute the people to these 2 floors such that both are non-empty. Now you can see the pattern, the probability that k is going to be equal to 3. Well, I'm going to choose 3 of my floors that people are going to stop at. And then for each of these combinations, I need to distribute my 12 people to these floors such that they're all non-empty. So I have 3 to the power of 12 total ways to do that. And now I need to subtract off the cases where at least one is empty. So inclusion exclusion again, I subtract the cases where only one is empty. There are 3 choose 1 ways for me to choose the empty floor. And then once I choose which one is empty, I have 2 to the power of 12 different ways to distribute 12 people to 2 floors. Now I've over subtracted the cases where 2 of our floors are empty, just inclusion exclusion. I need to add back on these cases. So I have 3 choose 2 ways to choose 2 floors to be empty, and then I only have 1 way to distribute 12 objects to 1 floor. So it's just going to be 3 choose 2 times 1. Now the probability that k is equal to 3 is just going to be 10 choose 3 times this number right here, which is 3 to the power of 12 minus 3 choose 1, I'll say, times 2 to the power of 12, and then plus 3 choose 2 times 1. So now let's just do it one more time with k is equal to 4, but you can see the pattern emerging here. Now the probability that our elevator stops 4 times, I choose the 4 floors out of 10 that our elevator is going to stop on. Once I do that, I need to distribute 12 distinct objects to 4 distinct floors. There are 4 choose 12 total ways to do that, but I've overcounted the cases where some of our floors are non-empty. So then I have 4 choose 1 ways to choose exactly 1 floor to be empty, and then I'll have 3 to the power of 12 ways to distribute my 12 people to these 3 floors. Now inclusion exclusion, I've over subtracted the cases where 2 of my floors are empty. How many ways are there for me to do that? Well, 4 choose 2 ways to choose 2 floors to be empty, and then when I have that, there's going to be 2 to the power of 12 ways to distribute 12 people to 2 floors. Now again, inclusion exclusion, I've undercounted the cases when 3 of my floors are empty, so I'm going to need to add back on the number of ways that I can choose 3 floors to be empty. I have 4 of them, so plus 4 choose 3, and then I'm going to have 1 way to distribute 12 people to 1 floor, so times 1. So now when I stop at 4 floors, I have 10 choose 4 ways to choose the 4 floors to stop at, and then once I've done that, I have this many ways to distribute 12 people to these 4 floors such that all of them are non-empty. Also, these are all probabilities here, so I should have been dividing them by our total number of outcomes, which would have been 10 to the power of 12, so I'll just add that in here. Now we've been doing this long enough to find the pattern here, right? Now let's try to write this as a formula. I was trying to find the expected value of a random variable k, which is just going to be equal to the sum from k, little k, going from 1 all the way up to 10 of k times the probability that k is equal to each of our numbers. So now that we've been doing this for a while, let's plug in the pattern that we've been seeing in 4 right here, which is going to be a little bit complicated. Basically, first things first, our total outcomes is just a constant, so I'm just going to pull that completely out of the equation right here just to make it a little simpler. And then pretty clearly, we're taking the binomial coefficient of 10 over k. Now let's turn this part in all of our equations into a general formula for k. So I'm obviously taking some type of sum here. Let's call our iterator here j. You can see that the things that are being iterated are this number within here and this number down here. It's also an alternating sum, so I'm going to have some -1 to some power, which we'll figure out. And then I'm going to have this binomial coefficient, which is going to be k choose j, our iterator, and then we're going to have this exponent right here. So it's going to be j to the power of 12. Now in all these cases, j is basically iterating from our value of k all the way down to 1. You can basically think about j being a value of 1 over here. So that tells us that j should go from 1 all the way up to our value of k. So when j equals 1, it's going to give us this term. When j equals 2, it's going to give us this term, which all checks out. So when j equals 1, I have this term over here. The reason that this number down here is 3 is because k choose k minus j is going to be the same as k choose j. So I could have also written this down here as k choose k minus j, which which is just the same thing as k choose j as I just said, but basically now all we need to find is the power that this -1 is being raised to here. So now you'll notice that when k is even, we have our j equals 1 term being subtracted, and when k is odd here, we have our j equals 1 term being added. So I can just raise this -1 to the power of k minus j, or I could do k plus j, it doesn't matter, it's just k minus j is going to look a little bit more like the binomial theorem, which we're going to need. Now this checks out because when k is 4, so an even number, and then j equals 1, well, we're going to get an odd number up here, and a -1 raised to an odd number is going to be negative, which checks out because now we have a negative over here. And then when k is odd, for instance, k equals 3, we're going to have j equals 1, and this is going to be an even number, and then we're going to get an addition just like we want. Okay, so now we figured out the general equation for this. It's just going to be right here, which is kind of a monster, and now we have to actually figure out how to simplify this, which is going to be even harder. So there are a bunch of random theorems that you can use to simplify this entire equation, but basically what I noticed first is that this term right here looks a lot like the binomial theorem. Right, I have my term raised to some power of k minus j. I have this k choose j, where k is here and j is our iterator, right? But the only problem is this j to the power of 12. Alright, so I had to look this up, but basically the cool thing that you can do here is notice that j to the power of 12, well, we want to get rid of this, right? We want something to the power of j for the binomial theorem. Alright, so bear with me here. J to the power of 12 is just equal to the 12th derivative of some dummy variable, which I'm calling t of e to the power of tj. Well, that's not equal to j to the power of 12, but it is equal to j to the power of 12 times e to the power of tj. But now if we evaluate this derivative at t equals 0, well then this is going to be equal to j to the power of 12. So the 12th derivative of e to the power of tj evaluated at t equals 0 is equal to j to the power of 12. And now we have j up here in our power, which is what we want. All right, so this is now getting complicated. I just plug this back in here for j to the power of 12. So now t is a dummy variable, which makes this a little bit easier. We can just pull out this 12th derivative and save this for later, basically, and the evaluation at 0. Now finally, this looks like the binomial theorem here. I can change the value of the starting iterator to 0 instead of 1, because when j would be equal to 0 here, this would just give us a term of 0. So there's no difference from starting j at 1 or 0. So by the binomial theorem, this term in green right here is just going to be equal to e to the power of t minus 1 to the power of k. Okay, so let me now just replace this, but the battle is not over yet because we still have a little bit of a ways to go. I'm just going to replace this over here, and then let's move this over to the middle. Okay, now this term right here also looks very similar to the binomial theorem. All I have to do is basically take 1 to the power of 10 minus k, and it looks exactly like the binomial theorem, just with this extra k out front. And I can do this because we're just multiplying by 1, so any power that I raise 1 to doesn't matter. Now the problem right here is this k, because it is our iterator, but we can use another formula with differentiation to get that to go away. But you'll notice that if I start the general binomial theorem here, the way I get a k down in front here is basically I can just differentiate both sides. So for here, I'm going to take a derivative with respect to x, so I can get the k down in front. So I take the derivative with respect to x of both sides. Over here, I'm going to get n times x plus y to the power of n minus 1. That's going to be equal to, when I take the derivative on this side, well, I'm going to have this n choose k again, and then I'm going to differentiate here. So I'm going to bring the k down, and then I'm going to have x to the power of k minus 1. And then over here, this is not going to change. It's going to be y to the power of n minus k. And now just to bring this back up to a power of k, I can basically just multiply both sides by x. When I multiply both sides by x, this will go back to being a power of k, and would you look at that? Now I can use this theorem right here to solve this right here, or at least simplify it. Basically, first of all, I can start this iterator at 0, because when the iterator is 0, we're going to have a full term in here of 0, so it doesn't matter if I start it there. Now I use this formula right here, where my x was the one that was raised to the power of k, so it's going to be my e to the power of t minus 1. So this whole thing in the green box, well, it's going to be e to the power of t minus 1 out here, and then my n in this case is going to be 10, right? 10. Now my x and my y are going to be 1 and e to the power of t minus 1, so I'm going to take e to the power of t minus 1 plus 1 in here. That's going to simplify to just being e to the power of t, and I'm going to raise that to the power of n minus 1, which in my case was 10 minus 1, so it's going to be 9. Now I'm just going to bring these down. Can't forget about these. Are constant 1 over 10 to the power of 12, and then don't forget I still have to differentiate 12 different times with respect to this dummy variable and evaluate it at t is equal to 0, but it's gotten a lot simpler. No more sums, right? All right, so new page. It shouldn't be too hard from here. I'm going to distribute this inside of here first. When I do that, I get 10 times e to the power of 10t minus 10 times e to the power of 9t. Okay, now let's just take the derivative with respect to t 12 different times in here. When I do that, I'm going to get 10. I'm just going to factor out the 10 first of all. When I take this 12 times, I'm going to get 10 to the power of 12 times e to the power of 10t minus right here, we took out the 10, so it's just going to be 9 to the power of 12 times e to the power of 9t. All right, now we still have to evaluate this at t equals 0. When we do that, this term's going to be 1, this term's going to be 1. On top, we're going to get 10 times 10 to the power of 12 minus 9 to the power of 12. And on the bottom, well, we're going to multiply by this, right? So we're just going to have 10 to the power of 12 on the bottom. Now, would you look at that? This is just going to be equal to 10 times 1 minus 9 on 10 to the power of 12, which is exactly what we got when we did it with the linearity of expectation, right? Yeah, thankfully I did not mess that up, but this is how you do it without using linearity. So I have no idea why I did all that, but I guess it was a good review of the Stirling numbers, and I guess we learned some new binomial things.